It is the second part of section 9.4, CNNs in practice. In the first part, we considered three basic ideas for CNNs: local perceptive fields, shared weights and biases, and pooling. These first two will make a convolution layer, and pooling makes a pooling layer. To form a complete CNN by putting all these ideas, we need to add some extra layers below the convolution pooling layers. Below this one, we need some extra layers. In this figure, we add the upper layer of 10 units, so that this is the simplest CNN network. And when we choose 20 of them, 20 features, then now we can choose that way. Filter shape is 20, and now that is the kernel is one-dimensional, two-dimensional, and 1 by 5 by 5. And after convolution, we are pulling with 2 by 2, which means that 2 by 2, 4 pixels will change it into 1. Okay. Then the number of parameters to teach for this simplest one is here. That's from the convolution layer. And now output of pooling is 20 of 12 by 12 feature map, and this is a bias, and that is 10 is here the neurons in upper layer. Altogether, it is more than 29,000. Along with this simplest CNN network, the classification accuracy is about 99%, but it's slightly less than 99%. For pooling layer, you don't need to train any parameters. Okay. For the simple network, you may add a second convolution pooling layer. And below here, you can add another convolution and pooling layer can be added here. Here now. Okay. It's added. Then let's say, let's choose 40 filters. Now input, output of that first convolution pooling layer is 20 of the feature map. So the input must be 20 dimensional in filter. And now 5 by 5 filter and 40 feature will be made. And pooling again 2 by 2. Then here the 12 by 12 and cut the side is 2 pixels, then 8 through convolution layer, and pooling will make a 4. So that 40 of 4 by 4 will be the output. And for the output, now you have to connect with this output layer. So that is the is counting the number of parameters to teach on the last layer. And if we add them, this is from first the convolution pooling layer, and that is from now second one. And then this is for the output layer, so that here altogether is about 8,000. It's way smaller than this one. However, the classification accuracy for the MNIST data set is now slightly larger than 99%. Now here, we may add another fully connected layer just before output layer. Okay. Now after adding, there's another convolution and pooling, and we may add one more here fully connected, and just over there, just before the output layer. Then the same way we can count the number of parameters to teach, and if we choose 40 neurons for that fully connected layer, so that we have 40 neurons just before the output layer, and also just below another convolution and pooling layer. Okay, then number of parameters to teach as 27,600. So yet is smaller than this one. However, now the classification accuracy becomes around 99.5%. That's the beauty of here the combination of convolution and pooling layers and fully connected layers. If we are using now ensemble of networks, then for example, using 5 CNNs, the same kind of CNNs, and 5 of them is made, and then for the output, we try to use majority votes, then here the accuracy becomes now 99.67%. Only 33 out of 1,000 is missed. Okay, here these are missed images. Here top right number is true label, and the bottom one is the predicted output. So here, as you can see over there, this one is more or less like a 9, but the label said is A. Here, easily we can say this is a 9, but it's only data has this as A. So except this kind of the images, everything else is well classified. So it is working very accurately and effectively. Now here we summarize the CNN. Intuitively speaking, it has better representation. The use of translation invariance through the convolution layer and will reduce the number of parameters it needs to get the same performance as the fully connected model. So it is because of this, the convolution layer, we can get better representation, even though along with a smaller number of parameters, we can get really good performance. And convolution kernels will try to detect local features and producing feature maps. So it's a geometrically localized features are detected by convolution kernels. And also through pooling, the information can be simplified from the output of the convolution layer, so that eventually the fast training is possible, and eventually this network will help us build deep networks using convolutional layers. Here we have to add, in many cases, fully connected hidden layers in between convolution layers. The fully connected hidden layers try to collect information for more widely formed features. And for convolution layer, it's localized features. And for fully connected hidden layer, now we try to collect information for widely spread features. Okay, here, finally, we consider deep learning packages. Here, the most popular one is CARATS. That is a high-level neural network and now application programming interface, so API. And it can run on top of TensorFlow, Theano, and here CNTK. That is Microsoft Cognitive Toolkit. And here, Keras focuses on being modular, user-friendly, and extensible, so that it's easy to use and easy to debug. And in fact, along with Keras, the debugging is almost not necessary. So it is very user-friendly and written in Python. Here, high level means that it is user-oriented. It's low level. The computational language is machine-oriented. So not necessarily high level is better. Low level is necessary. Here, C, for example, is a kind of low level language. But like a Python and or the other thing like MathTalent is a kind of a high level language. TensorFlow is second most popular package. It's covering low to high API levels, and it's an end-to-end open source deep learning framework developed by Google in 2015. The end-to-end means that including basically everything here. Also, it involves a symbolic math library so that eventually the network is so fast, very efficient. But TensorFlow is difficult to use and debug. And really, debugging is very hard. The TensorFlow itself is written in Python, C++, and CUDA. However, you don't have to learn about C++. You are using only Python to use it. And now, least popular one among these three is PyTorch. Now, the levels are from low to high API levels. It is a deep learning framework based on Torch, developed by the Facebook's AI research team in 2017. So it is relatively new. And last year, it was taken over by the PyTorch Foundation. It's a part of the Linux Foundation. It has outstanding community support and active development. PyTorch is much easier to use and debug than TensorFlow. And it's written in Lua. Okay, here we have a final remark. You don't need to learn C++ or Lua. Currently, Keras is most popular due to its simplicity and long history. And PyTorch is most rapidly growing. It can be viewed as a trade-off, the balance between Keras and TensorFlow. It is particularly good for natural language processing applications. Mathematicians and very experienced researchers will find PyTorch better than Keras for many applications. Okay, that's the end of the section and end of the chapter. Thank you.